So, hello everyone, welcome to our second guest lecture. So today we have Lola Thompson, and her talk is called Mind the Gaps Between Primes. Take it away.
All right, so thank you all for coming. So I should warn you before I get started that I actually have a cold right now and I'm losing my voice. So I will do my best to speak up, but if you don't understand something I'm saying, just unmute yourself and tell me to speak louder and I will try my best. All right, so, there we go. For some reason, I'm having problems with queuing slides. All right, so I thought because there's this new Jurassic World movie coming out, I thought I would go back to a quote from Jurassic Park, the original, which is DNA, the building blocks of life. And so if DNA is the building blocks of life, we think of prime numbers as the building blocks of integers. So a prime number is just a positive integer that is only divisible by 1 in itself. And every positive integer, except for 1, can be written uniquely as a product of primes. And so that's why we think of the primes as the building blocks that make up all the bigger integers. So primes are kind of mysterious, and they've been studied for a very long time, certainly going back thousands of years. And the thing that you might sort of think about when you make a list of primes, like you make a list of numbers and you highlight all the ones that are prime, is you might think, they seem to pop up kind of randomly. So that's one view people have of primes. And so people often say things like, well, the primes are kind of randomly distributed or they have no pattern. But on the other hand, they seem to have a lot of really interesting things show up. So for example, if you make this spiral that I made here, you could think about putting the numbers like 1 in the middle, and then 2, and then 3, and then 4, and then 5, and then you continue outwards in your spiral. And there's a dot everywhere that there's a prime. And you notice that the primes seem to fall on very specific diagonals as you spiral outwards. I mean, not always, but there definitely seems to be like something interesting going on there. It's maybe not as random as some people might claim. So anyway, what I want to pose to you in this talk is, the question, are the primes sort of random, or is it worth looking for patterns in the primes? And so I want to first give you a couple of cautionary tales. So here's the first one. In 1650, Fermat famously conjectured that all numbers of the form 2 to the 2 to the n plus 1, where n are the integers 0, 1, 2, 3, 4, etc., he conjectured that all of these turn out to be prime. And, he actually calculated it for the values that I listed here. And that's what led him to believe that this might be true. Well, then in 1732, Euler showed that Fermat's conjecture fails when n is equal to 5. So the very next number didn't work out. Unfortunately, this was back in the days before computers. And so Fermat was calculating all these things by hand. And so, it was really hard to get beyond 2 to the 2 to the 4 plus 1. But yeah, Euler disproved Fermat's conjecture. But then you might wonder, well, maybe it starts being true later on. And actually, as of 2010, I think was the most recent value calculated. It's known that this 2 to the 2 to the n plus 1 is composite for all values of n between 5 and 32. So if that's the case, then, you might even think, and some mathematicians have conjectured that it's always composite for all n that's greater than or equal to 5. And if that's true, then Fermat could not have been more wrong. So the reason I give you this cautionary tale is to say that just because something seems to be true at small numbers, it doesn't mean that it holds true forever. And so you have to be a little careful, because sometimes things are a little bit weird when you're working with smaller numbers, and then, the pattern looks like there's a pattern and the pattern doesn't continue as you're going out. So that's the first thing you need to be careful of when looking for patterns in the primes. My second story is, I'm going to mention a specific person, but this is actually the kind of thing that lots of people do. So there's this guy who calls himself Zoolog, and he's an American numerologist, mystic, self-proclaimed psychic. And he's also a self-published author and a self-described artist, musician, poet, and filmmaker. So a very versatile person. Anyway, I would wager he probably also wrote his own Wikipedia article. And he's someone who liked to dabble in mathematics. And so at one point, he posted a bunch of what he called important discoveries about the primes online. And one of his discoveries, so he put the positive integers into 2 columns. So he just started by saying, okay, we have 1, 2, 3, 4, like that, you know, going back and forth between the columns. And he said, wow, almost all of the numbers that are prime end up being in this first column. The only exception is the 2 that's in the second column. Another discovery that he claimed to make is he tried making 6 columns instead. And he noticed that all of the primes after the first row seem to fall into either column 1 or column 5. So let's talk about these so-called discoveries of Zolog. The first pattern, it's just stating that almost all of the primes are odd, which of course we know. The only even prime number is 2. I see there's a hand raised. Go ahead and unmute yourself if you've raised your hand, and you can go ahead and ask your question.
Yeah, isn't this, well, discovery sort of weird, because it seems sort of obvious that every column which has even numbers is bound to be composite except 2. So I don't really see what the, discovery is.
Exactly. No, this is exactly what I wanted to point out, that this guy's supposed amazing discovery is actually not so amazing when we think about it a little bit. But that's great that you noticed this exactly. So yeah, so the observation that almost all primes are odd is really not a deep fact. And yeah, so thank you for your point there. The second pattern maybe takes a little bit more thinking, but it will also be clear that all the primes should fall in column 1 and 5 once we think about it a bit. So let's kind of break this down. So if we, oh, sorry, go ahead.
Isn't it basically just saying that all the primes mod 6 are either just going to be 1 or 5?
Exactly. So I don't know if everyone here knows modular arithmetic or not, which is why I didn't want to put it in that language, but that's exactly right, that all of the primes are going to have to be congruent to 1 or 5 mod 6. And let me kind of go through this example that I've written now, which is exactly what you're thinking in your head. So for those who don't know modular arithmetic, we can just think about writing everything in column 2 in the form 6n plus 2, because notice how we go through multiples of 6 and then we add a remainder of 2, and that's what puts us in the second column. And so everything of the form 6n plus 2, we'll notice we can factor a 2 out of both the 6 and the 2. And so notice then that we have a composite number because we have 2 times something else. And the same thing is true for column 3. We write everything in the form 6n plus 3, and then we can factor a 3 out of both 3 and 6. And so you see here, we get 3 times another number. So that's also composite. And the same is true for column 4. We notice we can pull a 2 out of everything. And for column 6, we can pull a 6 out of everything. And so the only columns where we can't pull out a common factor from both terms are column 1 and column 5. And so these are the only possible columns where everything could be prime, where anything could be prime after the first row. So anyway, that's the idea that's going on. And so as we see, these are really not deep facts. We can restate Zolog's so-called theorem as saying that if n is at least 5 and it's prime, then n is not a multiple of either 2 or 3, which of course we know is true because that's what it, I mean, you can't have a prime that is a multiple of 2 or 3 if it's bigger than 2 or 3. So the conclusion here from my example is it's important to be a bit skeptical when looking for patterns in the primes, because you might either discover something that isn't true, or you might discover something that turns out to be completely trivial or well explained from the definition of prime, let's say, because I don't want to dismiss things as trivial. Anyway, so let's go ahead, now that we've talked about what makes something a good pattern versus not a good pattern, let's talk about some things that actually are good patterns in the primes. So first off, someone might ask, well, how many prime numbers are there? And it turns out that there are infinitely many primes. And so maybe some of you have seen this proof before, but I'm going to do the most classic proof. And so this one says, let's suppose that we have only finitely many primes. Then what we can do is we can write down a complete list. So P1, P2, P3, up to Pk, those are all the primes that exist. That's what we're supposing. So then what I'm going to do is I'm going to let this new number n just be the product of all the primes plus 1. And so we notice that because my number n is bigger than 1, then by my very first slide, we know that n is either going to be prime or it's a product of primes, because all the numbers bigger than 1 are products of primes. Or you could think of a number, that's prime itself as just being prime and maybe not a product of primes, or you could think of it as a product of only one number. Anyway, so the whole point is that you always have to have n being factorable into primes, or it's a prime itself. But if n is not prime, then we've actually found a new prime that isn't in our list. Because what this means is that since n is a product of primes, it has to be divisible by some prime that's not in our list. Notice that if P1 divided n, well, P1 can't divide n because P1 would also have to divide 1, because it's written in this form where we have a product of things plus 1. And so because P1 doesn't divide 1 and P2 doesn't divide 1, etc., then none of these P1 through Pk could possibly divide n. And so as a result, this tells us that either way, there must be another prime that's not on our list. And so our assumption that P1 to Pk was all the primes was false. And so that tells us then there must be infinitely many primes. So there's lots of different ways of proving that there are infinitely many primes. And so another possible approach you might take is you could look at the reciprocals of primes. So in other words, taking 1 over 2, 1 over 3, 1 over 5, etc. And you could add those all together. And it turns out that when you add all those together, you get an infinite number. I mean, it adds up, it keeps getting bigger and bigger and bigger forever. It never converges to anything. And so what this means then, notice how every term in my sum is a finite number. And the only way to add up a bunch of finite numbers and get infinity is if you had infinitely many terms in your sum. So that gives another, this is just a sketch of the proof. Of course, you'd have to actually show that this sum is infinite.
Yeah, I was about to say, how do you show that the sum is infinite?
So I don't actually want to get into that in this talk because I have sort of very limited time, but it's a great thing to look up afterwards. I want to get to like the main ideas. But yeah, feel free to look it up later. And if you want to talk about it, you can send me an email and we can talk about it. But it takes a little bit more work to show this. It's not as easy as the previous proof. So that's why I did the previous one. Anyway, so what I'm just telling you this fact because it's going to come up a little bit later in my talk. And so I want you to realize that, when we add the 1 over p's for all these primes p, that we do get an infinite number. All right, so what proportion of numbers turn out to be prime? That's another natural question to ask. Once we know there's infinitely many primes, we want to know, okay, among all the positive integers, what percentage of them turn out to be prime? And so if we look at just the first 100 numbers, notice how about 25 of them turn out to be prime. Those are all the ones I highlighted in magenta. And so, yeah, as we go through successive powers of 10 or alternating powers of 10 as it is in this chart, notice how the percentage of primes goes from 25% down to 12. And then it keeps going down smaller and smaller until we get to about 3%. And then, of course, as you can probably imagine, it looks like it'll probably still keep getting smaller, but that's as far as this table goes. And so we see that this percentage is shrinking and shrinking and shrinking. And so it turns out, actually, you might ask yourself, well, is 3% the correct percentage of primes? And it turns out that it was actually proven that if we look at the number of primes between 1 and x, that this function grows like the function x over the natural logarithm of x. So that's what this means here. It means if you've taken calculus, it means you take the limit as x goes to infinity of the number of primes up to x divided by x over the natural logarithm of x, and that is equal to 1. And so when we see that this limit is equal to 1, it tells me that the function in my numerator and the function in my denominator grow at the same rate. And so that tells me, in other words, that pi of x behaves like x over log of x. And so if we think of this in terms of percentages, it's saying that among all the numbers in the interval from 1 to x, of course, there's x of those, that 1 over log of x will turn out to be prime. And of course, we know that if we take the limit as x goes to infinity of 1 over the natural log of x, then that's going to approach 0. And so in other words, it tells us that about 0% of all positive integers work out to be prime. And so I think this is a really cool fact, right? There's infinitely many primes, but if you throw all of them, and if you throw all the positive integers into a paper bag and you draw one out at random, the chance of getting a prime is 0. Anyway, all right, so now what I really want to focus on in this talk is an object called a twin prime. And so this, of course, is tied with a famous conjecture, but let's first look at twin primes. So I went back into my chart from earlier, and I just highlighted all of the pairs of primes that differ from each other by 2. And so those are the blue ones. And so we can see that there are fewer twin primes than just primes. But it turns out that if we go really far out, like here are 2 really big numbers, that this is a pair of twin primes. And so this begs the question, well, how many twin prime pairs are there? Will we keep finding more and more of them, or is there some largest twin prime pair? And so this sort of question was first posed in a textbook by someone named Alphonse de Polignac. So I think a lot of people think this conjecture, the twin primes conjecture, that there are infinitely many pairs of twin primes is like this 1,000-year-old problem or thousands of years old problem. But actually the first time it was written down in a book was in 1849. And it was this textbook by Alphonse de Polignac. And he said the following conjecture. He said, for even integers h, there are infinitely many pairs of consecutive primes, p and p plus h. And so this, of course, is a stronger conjecture than just the twin primes conjecture, because it's saying that every even integer can appear as a gap between primes. So you could have p and p plus 4, p and p plus 6. There should be infinitely many pairs of this form. I should point out that this is not actually Alphonse de Polignac. So back in the era before photographs, of course, a lot of mathematicians didn't have their pictures available. And so I found this picture of Alphonse de Polignac's father. So he was a French dignitary. And so as a result, he had this fancy official portrait done. And I'm just hoping that Alphonse looked a bit like his father. So I put that picture there just to give you some sense of what he might have looked like. All right. So let me now tell you a bit about the recent work on bounded gaps between primes. So in 2003, so we're going forward from 1849 to 2003, Dan Goldston and Cem Yildirim announced a proof that there are infinitely many pairs of primes that differ by at most 12. And unfortunately, their proof turned out to have a really serious error in it, which was found by Andrew Granville and Sound. So they unfortunately, couldn't just say, okay, we're finished. We found infinitely many pairs that differ by at most 12. However, they got together with a third author, and the 3 of them, so Goldston, Pince, and Yildirim, showed that if they assume a big unsolved conjecture, this is called the Elliott-Halberstam conjecture, if that turns out to be true, then there are infinitely many pairs of primes that differ by at most 16. So notice how this is a lot worse, really, because not only do you go from 12 to 16, but you have to assume a big unsolved conjecture is true in order to prove a different unsolved conjecture. So maybe that's a bit dissatisfying to you. But this was believed to be really the furthest that things could be pushed. And, a lot of number theorists felt that in order to get any closer, in order to get something that doesn't depend on an unsolved conjecture, or in order to get any smaller than 16, that one would really need some major new tools that hadn't been developed yet in mathematics. And so the interesting thing is that not too long later, so in 2013, Yitang Zhang announced that there are infinitely many pairs of primes that are at most 70 million apart. And this really kind of stunned the mathematics community, because a lot of people really, thought that this had been pushed as far as possible using the methods we currently have, and that anything new would require lots and lots of new technology to be developed. But, it was kind of amazing. He was able to push what they did just a little bit further. And it's an interesting story, because he wasn't sort of your typical high-profile mathematician. So first off, he was unable to secure an academic position after earning his PhD. And so he ended up doing a bunch of odd jobs instead. So he worked as a sandwich artist at Subway. He worked as a motel employee in Kentucky. He also delivered food for a restaurant in New York City. And then eventually he took a position as an adjunct professor at the University of New Hampshire. And so it's important to know that adjunct professors, they're being paid for their teaching, but they're really not being paid to do research. And in fact, they often have very high teaching loads and not a whole lot of time to do research. And so it's sort of amazing that someone with so little time for research came up with this amazing result. In addition, he had only written 2 other papers during his whole mathematical career, and he was already in his late 50s when he made this discovery. And there's a bit of a bias in math, which hopefully we're getting away from, that a lot of people do their best work when they're young. I think that this is actually a huge misconception, and that it's very possible for people to do good work later. But it still was kind of amazing that somebody with, not a whole lot of track record in his late 50s suddenly came out and did this amazing thing. So what I want to do in this talk, I'm not going to tell the whole proof that Zhang used, because it's way beyond the scope of this talk, and it also would probably take me like many hours. But what I want to do is tell you about one of the key techniques that is used in his paper. And so in number theory, there's this method called sieving, which is used to filter out numbers that have certain properties that we like from a larger list of numbers. So you can think about it like when you're making pasta and you have like sauce and pasta in a pan, and you pour it into a colander and you shake it around and all the water goes out and you're just left with the pasta. Or when you go to the beach and you have like sand and seashells, and you sift it in a plastic tool, and then all the sand goes through and you just have the seashells. So this is what we mean by sieving. We're basically going to sieve out the numbers we don't want and be left with the ones that we do want. So, Okay, so this is the sieve of Eratosthenes. And so what you do is you circle the number 2, and then you cross out all multiples of 2, because those can't possibly be primes since they're divisible by 2. And then we do the same with 3. We circle 3 and we cross out all multiples of 3, because again, those can't be prime. And then we circle 5 and cross out bigger multiples of 5. And then we circle 7 and we cross out bigger multiples of 7. And then everything remaining on our list has to be prime. And that's because if we go up to the square root of n, so here my n appears to be 120 actually. So when you go up to the square root, I don't know why I did it to 120. It should be easier with 100. But anyway, let's pretend we're just working with 100 because the square root is easier. So let's say we go up to 100. And if you take the square root of 100, that's just 10. And you notice that you can't have 2 numbers bigger than 10 that are both prime factors of a number that's less than or equal to 100. Because if you multiply together 2 numbers that are bigger than 10, then their product is going to automatically be bigger than 100. And so, of course, you can do the same thing with 120. I just wanted to pick a nice, easily square rootable number there. Anyway, so this gives us a nice way of efficiently finding a list of prime numbers. And so that's one form of sieving. It gets rid of all these composite numbers and you're just left with primes. Another form of sieving is called inclusion-exclusion. And so this is where you have, let's say you want to count all the elements inside this set. And so we call this set A union B union C because it's everything that lives inside these 3 circles put together. Well, one way of doing this is we count everything inside of A, and then we count everything inside of B, and we count everything inside of C. But notice that when we do that, we have counted this kind of football shape in the middle. We've counted that stuff twice because we counted it in both A and B. And same thing with A and C, we counted this football shape twice. And so that's also a problem. And same thing with B and C. So in other words, we have double counted each football shape that is called the intersection of A and B, or A and C, or B and C. And so what we have to do then is we have to subtract out 1 copy of each of those so that we're not double counting the overlap. But then notice that this triangle in the middle has been treated in kind of a funny way. So we've added the triangle in 3 times, once when we added A, once when we added B, and once when we added C. But then we've subtracted it 3 times when we've subtracted each of these football-shaped intersections. And so now we have to add the triangle back in at the end because we don't want to subtract out, we added 3 copies and we subtracted 3 copies, so they all got canceled out. And so that's why we add this last part down here. So this is called the inclusion-exclusion formula because you're going back and forth adding and subtracting things. And so let's look at a number theory question that uses inclusion-exclusion. So we could ask the question, how many integers between 1 and 100 are not divisible by 2, 3, or 5? And so what we can do, we can define our 3 sets. We'll look at the numbers divisible by 2. That's what this symbol here means, is 2 divides n, so numbers divisible by 2. And then we look at the set of numbers divisible by 3, and then numbers divisible by 5. So those are my sets A, B, and C. And so if I want to know how many numbers are divisible by 2 going up to 100, well, I just take 100 divided by 2 and I get 50. Now, if I want to know how many numbers are divisible by 3, I have to be a little careful because 100 over 3 is not an integer. It's 33.333333 repeated. And so we ignore the decimal part and we just take the integer that's directly below that. So we get 33. And similarly, the numbers divisible by 5, well, that works out nicely. We just get 20. So these are my counts, my number of elements in A, B, and C. And then I can do the same exact stuff to find how many elements are in the intersection. So if I have 100 divided by 6, that tells me the number of numbers that are divisible by both 2 and 3. And same thing with 15 for both 3 and 5, and 10 for both 2 and 5. And then finally, if I want to know how many numbers are divisible by 2, 3, and 5, I multiply those together, I get 30, and I take 100 divided by that and pick the next integer that's below that, and I get 3. So that gives me all the ingredients for my inclusion-exclusion formula. And then the last part that we need to think about is I'm going to take this quantity that I just found, but I'm going to subtract it from 100 because we asked how many are not divisible by that. And so it's everything in my set minus the ones that are divisible by 2, 3, or 5. And so that's where we end up getting 26 in the end. So this just gives you a flavor of 2 types of sieves that we use in number theory. And using a more complicated version of the sieve that I just showed you, the inclusion-exclusion, we have a fancier sieve called Brunn's sieve. And Brunn's sieve you can use to show that the number of twin prime pairs, p and p plus 2, where p is at most x, that this quantity is bounded above by 100x divided by log of x squared, as long as x is large. And so as a consequence of this, pairs, that actually when you add all these reciprocals together, that it adds up to a finite number. And so this might be a bit surprising if you go back to our proof, our second proof sketch, that there are infinitely many twin primes, because remember that the sum of the reciprocal of all primes was infinity. And that's what told us that there were infinitely many primes. You might be tempted here to look at the fact that this sum converges and to think, okay, maybe this means there's only finitely many twin prime pairs. But actually that wouldn't be true, or at least you can't conclude that from this evidence, because maybe it's the case that there's infinitely many terms in this sum, but just that the terms get really, really small really quickly. So if you've taken calculus 2, maybe you looked at some infinite sums like the sum of 1 over n squared, for example, for integers n from 1 to 100. And maybe you saw that 1 to infinity, sorry. And maybe you saw that this adds up to a finite number. It's the same kind of thing here. So it doesn't tell us that there's only finitely many terms in our sum. It just tells us that maybe the terms decay really quickly. So anyway, so twin primes are a bit mysterious. Okay, so what is it that Goldstine, Pintz, and Yildirim did? Well, they developed a new sieve, and their new sieve is now called the GPY sieve. And the sieve is really nice because it detects numbers that are plausible candidates for having prime pairs in them. And so what it does is it throws away almost all numbers, but the ones that it keeps are numbers that are likely to be prime and also closer together than average. And so by keeping only numbers that are close together and very likely to be prime, then they end up with a set that they can work with that ends up being useful in proving the fact that you can get infinitely many pairs of primes that have some bounded distance between them. And so that's basically the model that Yitang Zhang modified. And yeah, his modification is a bit complicated, so I don't really want to get into it in this talk, but it has to do with sort of understanding whether the primes are uniformly distributed among residue classes mod Q, if you know about modular arithmetic. That's the basic idea. So I'll just sort of say that, and you know, I'm happy to talk more about this maybe later. So what I want to now do is talk about progress that happened after Yitang Zhang. So Yitang Zhang, like I said, his result was released in May of 2013. But there was actually a lot of exciting stuff having to do with gaps between primes in 2013. And so now I'm going to talk about something called prime K-tuples. And it's natural to wonder whether there are infinitely many tuples of primes. So not just pairs of primes, but you could have, for example, triples or quadruples or quintuples. My students often ask me if I mention things like the Twin Primes Conjecture, a lot of them say, well, what about like a prime triples conjecture? And I say, well, what do you mean by that? And a lot of times they say, well, what about P plus 2, and P plus 4? Because these are kind of natural, it's a natural extension of thinking about twin primes. But it turns out that these can't be simultaneously prime infinitely often. And so you can actually think about this for a minute and see, is there some divisibility issue that would prevent this from working out? Maybe I'll give people a few seconds to think about it and see if anyone notices the issue of why these can't all be prime infinitely often. It's like a good time also. Oh, I see hands raised. Great. So the first name I see is Leo. Do you want to say?
Wouldn't it be like because one of them has to be a 0 mod 3, so one of them has to be divisible by 3, so they all three can't be all prime?
Exactly. So you're right. No matter what your prime is congruent to, so if your prime is bigger than 3, then it's either congruent to 1 or 2 mod 3, or if you don't know about modular arithmetic, then it means your prime is it's in the form 3 times m plus 1 or 3 times m plus 2. So if your prime is of the form 3 times m plus 1, then notice that when you add 2 to it, then it's going to be of the form 3 times m plus 3. So then that's divisible by 3. And on the other hand, if your prime is of the form 3 times m plus 2, well, once you add 4 to it, then it's going to be divisible by 3. You can see that you can, did I do that right? Let's see. So you have 2 plus 2 is 4, that's 1 mod 3, and then plus 2 more gives me 3 mod 3. So yeah. So anyway, you see that either way, regardless of what you start with for your P, that if you add 2 or you add 4, that one of those is going to have to be divisible by 3. And so they can't be simultaneously prime infinitely often because the only prime divisible by 3 is 3 itself. All right, so that's why we sometimes have this obstruction. So you can't possibly have all K tuples having primes infinitely often. or being all prime infinitely often. So this is for anyone who hasn't seen modular arithmetic, because I know that people have different backgrounds here. But when we've been talking about mod M, we're really thinking like you have a clock, and the clock that we normally think about having on our wall has 12 numbers going around it. But rather than writing a 12 at the top, we write a 0. And all the time you're actually doing modular arithmetic without even realizing it. So when you tell time on a clock, you know, afternoon, if you're not living in Europe, at least, then you might say it's 1 o'clock or 2 o'clock. Here in Europe, we tend to say sometimes 13 or 14. But in the US, typically, rather than continuing with all 24 hours, you often wrap it around and you say, okay, it's 1 o'clock in the afternoon, it's 2 o'clock in the afternoon. And that's exactly what this means down here. So we say that A and B are congruent mod M if they have the same remainder when you divide them by M. And so you see here that 13 and 1 both have remainder 1 when you divide them by 12. And same thing with 14 and 2 or 15 and 3. And so this is what we've been talking about when we've been saying various congruence things mod M in this talk. Okay, so I bring this up because this gives us some insight into which k-tuples are not possible, which ones can't be prime infinitely often. So we will say that a k-tuple, h1 up to hk, of non-negative integers is called admissible if it doesn't cover all the possible remainders mod p for any prime p. And so I'll give you an example to say what I mean by covering all the remainders. So for example, this tuple here, 0, 2, 6, 8, and 12, this is an admissible 5 tuple. And so we'll just go through and check that there's always at least one remainder that is not in this list. So for example, mod 2, you see that all of these numbers are even. So 1 mod 2 gets skipped. And so we see then that it's not covering all possible remainders mod 2. And similarly, mod 3, you see we have 0 mod 3, 2 mod 3, 0 mod 3, 2 mod 3, 0 mod 3. So we never get 1 mod 3 in this list. And you can go through and check mod 5 and mod 7. And eventually you get to a point where your number is bigger than the number of elements in your tuple. And so then there's always going to be some remainders not covered. And so anyway, what this means is once you check that there's always at least one remainder not covered mod p for any prime p, then it is in fact possible to get an infinite tuple of primes, or at least there's no obvious obstruction preventing that. And so what we're going to do in the rest of this talk is we're going to restrict ourselves to only these admissible k-tuples, and we're not going to worry about the problematic ones like p plus 2, p plus 4, and p. So there's a conjecture of Hardy and Littlewood, which is called the prime k-tuples conjecture. And it says that if you have an admissible k-tuple, so the kind we talked about on the last slide, then there are infinitely many integers n, so that all of the numbers n plus h1 through n plus hk turn out to be prime. And so this is something we still don't know if it's true or not. However, in November of 2013, so 6 months after Yitang Zhang's amazing discovery, there was a paper on the archive by James Maynard, and apparently Terry Tao, who's in the other picture, had a paper in the works that was doing basically the same thing. And so I'm giving them both credit here because they were both so close. And it says the following. It says if m is at least 2, then for any admissible k-tuple, if you have h1 up to hk, where k is sufficiently large, then there are infinitely many integers n, so at least m of the numbers n plus h1 through n plus hk turn out to be prime. So it's not saying that everything is prime. It's not proving the full prime k-tuples conjecture, but it's saying at least m of these numbers, and we don't know which m will turn out to be prime. And so it's still, it's stronger than Zhang's result, because Zhang's result produced pairs of numbers that were prime, that were some bounded distance apart. And this is giving us more numbers that are prime, that are some bounded distance apart. So using Maynard and Tao's work, this group of mathematicians got together on the internet, kind of like Wikipedia, you know, where you crowdsource something, and they all worked on separate little pieces of basically using Maynard and Tao's ideas to try to trim this number down from 70 million that Zhang announced as the gap between primes, and they got it all the way down to 246. And so this was the state of the art in February 2014, and it's actually still the state of the art today. So we know now there are infinitely many pairs of primes that are at most 246 apart. And so in other words, if you know the pigeonhole principle, this says that there's some number between 2 and 246 that appears infinitely often as a gap between primes. And of course, this isn't as good as the Twin Primes Conjecture, but you know, it's still a lot better than before 2013, when we didn't know of a single finite number that could be the gap between primes infinitely often. All right, so now what I want to do is tell you a bit about some of my own work. And so I'll mention kind of 2 applications of this method of Maynard and Tao into problems that I've thought about. So remember back on my first slide, we talked about primes being the building blocks of the integers. And so one question we could ask is, what are the building blocks of polynomials? Does anybody know what you use to make other polynomials? It's sort of a word for this. Someone wants to unmute themselves, they can say it. If not, I'll give you the vocabulary word. And unfortunately, I see the chat blowing up, but I can't actually see the chat without having it show up on the screen, and then it kind of blocks the slides. So please unmute yourself if you know the answer and just say it out loud, because I don't want to block the slides too much.
I was gonna say binomials.
What was that? Binomials? So binomials are a type of, did I hear you right? Binomial? Monomial. Yeah, so not exactly monomials, because I'm not going to restrict myself here to monomials, but there's another type of polynomial that is kind of the smallest unit in the polynomial world. And maybe people just haven't seen this terminology. I don't know.
I guess, like, if you think of it like in a linear point of view, as in then monomials, I mean, it's a linear combination of monomials. But if you're talking about like factoring, then then irreducible polynomials.
Yeah, that was the word I was looking for. So we think about just like building up all the bigger integers with products of primes. We think about building all polynomials from irreducible polynomials. So every polynomial can be factored into a product of irreducible polynomials. And those are going to be the objects that we're working with now. So that's what I was looking for, but maybe my question wasn't so clear. So for example, if we have x cubed minus 1, well, we can factor that into x minus 1 times x squared plus x plus 1. And as hard as you try, you can't factor either of those any further, at least not with integer coefficients. There's some other things you might do with other coefficients, but we're not going to worry about that. We're just talking about polynomials with integer coefficients. Okay, so I have factored x cubed minus 1 as far as possible. And just like we took integers and we reduced them mod p, we can do the same thing with polynomials mod p. So you see here, I have the polynomial 4x squared plus 5x plus 1, and I want to reduce this mod 3. And so that just means reducing the coefficients mod 3. And so if we do this, we notice we just get x squared plus 2x plus 1. And then it turns out actually that once I reduce it mod 3, it actually becomes something that can be factored. So notice how this is the same as x plus 1 squared. So anyway, sometimes things that didn't look factorable or that weren't factorable with integer coefficients, once you reduce them mod a prime, you actually can factor them. So in my result that I'm about to show you, we will be thinking in terms of these polynomials mod p, and we're going to call zp the set of integers mod p, and we're going to call zp bracket x the set of polynomials mod p. And so when I write zp bracket x, think about doing things like this, where we're taking the polynomial and then reducing it mod p. Okay, so there were 2 people at Princeton who wrote dissertations on a similar topic, actually. So there was Chris Hall and there was Paul Pollack. And so Chris Hall showed that if P is greater than 3, then any integer A in ZP, except for 0, can occur infinitely often as a gap between irreducible polynomials. And then Paul Pollack showed this for the P equals 3 case as well. And so this was considered to be the, nice result that is sort of the twin primes theorem for polynomials. So notice how a number like 2, if it's inside of ZP, so if P is at least 3, which is the condition here. So a number like 2 then could appear infinitely often as a gap between irreducible polynomials. And so you do get infinitely many pairs of irreducible polynomials that differ by 2. So this is the twin primes analog in the polynomial world. And so one thing that my co-authors and I were interested in doing, so I still worked with Paul Pollack and Chris Hall from the previous slide, but it was also with me, myself, and Robert Lemke Oliver and Abel Castillo. We realized that we could take the ideas of Maynard and Tau for getting bounded gaps between primes, and we could prove an analogous result for bounded gaps between irreducible polynomials. And so we showed that if you have an admissible K-tuple, so again, something like H1 through HK that don't have any of these congruence obstructions, and these elements in my tuple here actually don't have to be numbers, they don't have to be integers, they can actually be polynomials in ZP adjoin X. And if we have a sufficiently large integer K, this is just like the Maynard and Tau result, then there are infinitely many polynomials F living inside ZP adjoin X, so that at least M of the polynomials F plus H1 through F plus HK turn out to be irreducible. And so the important thing to notice here is we're not just getting numbers as gaps between polynomials, we're getting actually polynomials as gaps between polynomials. And we're even getting a lot more examples than Chris Hall or Paul Pollack in their paper. So their paper is constructive, and it kind of, the examples they get kind of jump up in degree very quickly, and we get like a lot more of a given degree with the Maynard and Tau method. So anyway, this is an improvement on what Chris Hall and Paul Pollack did in their PhD theses. Another application of the Maynard-Tau method that I want to talk to you about, I'll kind of introduce the problem and then I'll tell you what we're able to do. So we will let S sub g of n denote the sum of the base g digits of an integer n. And for example, if you look at the numbers 523 and 541, these are both prime numbers. In fact, they're consecutive prime numbers. And if you take their digits, you notice that they both add up to 10. And so Sierpinski, who was a Polish mathematician, asked in 1961, are there arbitrarily long runs of consecutive primes P where this digit sum is constant? So like we had here where we got the same number twice. Or can we get arbitrarily long runs where the digit sum is increasing? Or can we get arbitrarily long runs where the digit sum is decreasing? So he was curious about all three of these questions. So you notice here we did this with base 10, but he's asking a more general question with base G, if you want to do things in base G. All right, so that was the question that Sierpinski posed. And let me give you a brief history on this question. So Sierpinski showed that you could have pairs where the digit sum is increasing infinitely often. And then Paul Erdős, who was a Hungarian mathematician, showed you could have pairs, this was 1 year later, where the digit sum is decreasing infinitely often. And then Sierpinski in 1968 decided to one-up Erdős and show that if we assume, again, another unsolved conjecture, because number theorists love to do this, where we like to assume unsolved conjectures to prove other things. So if we assume an unsolved conjecture called Dixon's prime K-tuples conjecture, then we can get triples of digit sums that decrease infinitely often. And then another Polish mathematician, Schinzel, in an unpublished claim said, well, okay, if you assume hypothesis H, which is another unsolved conjecture, then we can get arbitrarily long runs of consecutive primes P where the digit sum base 10 is increasing, or you can get arbitrarily long runs where it's decreasing. So this was kind of what people had been able to show before us. And my co-author and I realized that we could actually put together some ideas from Maynard and Tao's proof, along with some results on digit sums. And we could actually show that for any base G, there are arbitrarily long runs of consecutive primes where the digit sum base G is constant, or similarly, you can get the result where the digit sum is increasing, or similarly, you can get the result where the digit sum is decreasing. So we can get any of those three. And so the important difference to notice between our result and what came before us is we don't have to assume any unsolved conjectures. So our result is completely proven without assuming anything that's not known. And then we also extend it not just to base 10, but actually to any base G. And so we sort of finished off this question of Sierpinski finally after, let's see, going from 1961 until 2015. So anyway, I wanted to go ahead and end my talk there. And this, yes, this is my co-author and I dressed in Star Trek uniforms. We went to a conference near a place called Vulcan, Alberta, which is a Star Trek themed town in Canada. And we just couldn't resist taking this picture. So anyway, I'll go ahead and end my talk there. Thank you very much for listening.
Okay, well, thank you for a great talk. So are there any questions now? So I guess if you have questions, if there's some in the chat, I can relay them. So here's a question. Why don't we consider that there are infinitely many pairs of primes which differ by at most 16 now that the Elliott-Halberstam conjecture has been proved?
It actually hasn't been proved. That's the tricky part. So you're right. It would be awesome if you had the Elliott-Halberstam conjecture, but the full version that you need for this has not been proved.
Here's another question. Can you explain the GPY sieve in further detail?
So that would be quite. I don't think we really have time to get into that here. Yeah. So maybe it's just worth saying that maybe the way that it's used. So in all of these problems, including the digit sum problem that I just talked about, one of the things that people do is they kind of pre-sieve the set of numbers so that it has only things that are likely to have the property that you want. And so we end up using actually the GPY sieve to kind of pre-sieve a set so that the digit sums sort of have the properties that we want, and the numbers that are left in our set are likely to be prime. And so it's the same kind of thing that I mentioned in my overview slide, but actually getting into the technicalities of the GPY sieve, it gets quite complicated. So I don't think that that's something that I want to do like an impromptu lecture on, especially if people have to go at some point. But yeah, it's really the GPY sieve plus showing that the primes are uniformly distributed mod Q for Q going up to about x to the 1/2. Those were the two key ingredients that Zhang needed. So Goldstein, Pince, and Yildirim were able to get almost to x to the 1/2, and there was kind of considered to be this barrier that if you could show that the primes are uniformly distributed mod Q for Q a little bit bigger than x to the 1/2, then you could actually use their sieve to fully get bounded gaps between primes. And so what Zhang did, maybe this is an interesting thing to know, is Zhang actually showed that he could add some extra conditions to his set, like only looking at numbers that only have small prime factors, like values of Q that only have small prime factors, and only looking at, what was the other condition? Maybe that Q is square free or something like this. So he put some extra conditions on the values of Q. So he didn't look over all values of Q. And by putting these extra conditions on, he was actually able to push this barrier a bit higher and show that there was uniform distribution mod Q, even for Q a bit bigger than x to the 1/2. So that's kind of as much as I feel like I can really say without like launching into a very long discussion. But I hope that's satisfactory.
Yeah, okay. Next question is continuing on the Elliott-Halberstam conjecture, isn't the Bombieri-Vinogradov theorem considered to prove it for some bounded value?
Yeah, so exactly. So Bombieri-Vinogradov proves it for Q going up to x to the 1/2. And that's the thing. So Elliott-Halberstam says you can actually get this uniform distribution going all the way almost to 1. And unfortunately, Bombieri-Vinogradov, which has been proven, only shows it going up to x to the 1/2. And so that's kind of the gap is between x to the 1/2 and 1.
How is the digit sum question related to the twin prime conjecture?
So the whole point is it's not the problems themselves aren't related. It's really the methods that are related. And so the key idea that we had, the reason that I brought this up is because we use the same kind of pre-sieving that you see in the GPY sieve. So it's not an application of the conjecture itself, or it doesn't have any relationship to the conjecture, but it's just that we use this GPY sieve, which we thought was super cool, in order to pre-sieve our set to have the properties we wanted. And then we were able to get a result that I mentioned here.
Great. So are there any other questions?
I can stop sharing so I can like see people one more time before I leave. It was nice to get to join you all from wherever you are in the US, presumably. Greetings from the Netherlands. Are some people not in the US?
Yeah, quite a few actually.
Oh, cool. Wow. Okay, so very international group, just like me. So I'm here in Utrecht in the Netherlands. So yeah, nice to meet you all. And you know, if you do have further questions, you can feel free to email me. I realize I didn't have time in this short talk to get into all the details. But I also have some slides on my website where I give more detail when I gave these kinds of talks for a more of a professional number theorist audience. And, you know, then I do give more details of things like the GPY sieve and stuff like that. What's my email address? So I will go ahead and type it in the chat. The other thing too is I know there's a Discord channel, so I could join Discord, and then maybe if people have questions, I could answer them there, because then I won't be writing the same email to different people. I can just like write it in one place. That sounds probably more logical.
Yeah, let me send you a new invite link for the Discord, because the other one would have expired.
All right, that sounds good. So I can use this Discord link. I'll sign up after we log off because I feel weird doing it while we're talking. But yeah, thank you all for coming, and I hope that you're excited by number theory like I am. Thank you.
Yeah, so thanks. So that's all for that part of the class. So you can go now.
All right, bye everyone.
Bye. Thank you.
Thank you.
Thank you.